Oh, yes, then this 2018 further clip 008. Yes, so just continue from the lessons we have last time. Hopefully this time will be better because I'm using the microphone and hopefully the sounds would be better. What we're doing today, basically, we have discussed a little bit of residual block, and the purpose of residual block is about whether you find the graph is linear or not. For example, if we've got a graph in like this one, we can really see this pattern is a straight line, and in terms of residual plots, you would be able to see a plot is pretty good, random distributed and certain way that you have points above and below and would have this particular um, residual plot come up, and which is a good thing. When we have such a good graph, then we don't need to worry about anything, and we can use it to project or to do the interpolation and extrapolation straight away. However, if we've got a graph that's not like this at all, and instead of a straight point, let's say we have those points coming, become quite flattened. And you can see instead of going straight up, those points is start level and become a bit flat. So if you're looking at those situations, our residual plot would be having a big problem after certain point. For example, when you try to look at that, the residual plot is quite normal initially, and you will find the majority of your point will be above, and it sides a little bit down there, and you can see the graph kind of like getting up there, instead of having a nice random distributed graph. And we know that this is not a good patterns that we're looking for. When it's not linear, so very important to remember that when it's not linear, it doesn't help us to do any projections. There's hard to do, there's not good for predictions, CTION, predictions. And if we can't do any prediction, that we need to do one thing, and which come down to the most difficult part of our course, which is what we call um, transformation graph. Transformations. Transformation means one thing, which is trying to do and modify the data that we have, such as the one that above here is nonlinear. And what we do, there's one purpose for transformations, try to make that more linear. And more linear help us to realize that's yeah, the projection would be good. Now, just go back to the data we have before. We have all this data pretty good and suddenly get kind of very flat at the end. So if you're looking at this particular graph and we can do certain things to this graph, for example, if this going straight up, that would be good. But now we have that one going flat. We've got a problem along here. So let's highlight it into yellow. We've got a problem along this point, and this point is kind of too small. In terms of a graph, for all transformation, we generally have two actions. One actions, we call them compress. The other actions, we call them stretch. So for compressing a graph, we basically try to make the value smaller. For stretching the graph, we try to make the value bigger. Okay, so stretching is making bigger and compressing is getting down. And in each of the action there, you can try to compress the x side. What is x value? X value is along these independent variables. For independent variable, that x is there. If you compress the x, that means you try to draw the point closer and closer. If you try to draw the point closer, then I like to saying that is horizontally, you move the x value or move the point or data closer to the zero. Or you can do the other actions for y. When you try to do compress for y, you bring it down. Make sense? So normally, let's say the y values, the dependent variable is 100. When you compress the y values, it becomes 10. Okay, so compressed is one of the action to change the data. And it seems like, how can you change the data? There's some mathematically way that if you do all the mathematical way, like you divide the whole data by 2, then every single value is dropped by 2. So when you have the same action for every single entries, that means we don't really worry about we will have a wrong. We're still looking for the trends, but it's just one more steps for us to do calculations. Then after compression, we can look at stretch. Doing a stretch, it could be either x or y as well. If you're saying compress is getting the x smaller, then that means when you stretch it, which is opposite, you try to make the x a bit bigger and make the y increase. Right? There's always a kind of four action that we can do, either x compress, y compress, or x stretch or y stretch. Let's have a look at the situation that we've done in this graph. If we look at the very first situations, which is compressed at the x, we have all the points here highlighted yellow. Then what do? If we compressed? We try to bring all the data closer. So if let's say all this data, bring it there, becomes that way and closer and closer, you will find that those dots would becomes strict, move across from the highlighted yellow into the highlighted blue area here. So those highlighted blue would be the after transformations. Once we change the values, kind of compress the x values, we bring those highlighted yellow points into the new region. And these regions help us to see there's a bit more linear relationship. As this is a more linear relationship, we call this a good move. So number one, basically we'll say that yes, is good to help. It would help us to make a nice kind of curve. So how about we try to look at the other actions? So instead of getting compressed x, try to look at what happened when we compress y. So have a look. If we compress y, try to use green. So this is your second actions. If you compressed y, and what does that mean is we've got the problem of this region. And what we can do when we compress y, we bring all the data down. So instead of making that, you're changing those dots into here. And after when you can see a particular trend here, we expect that to like a straight line, but now you're coming down. So that means it's not helpful at all. Does it serve our purpose? The things that we want to do is a more linear graph. This is after this y transformation, after you compress the y values, it's not really changing, it's not helpful at all. So that number 2, according to this, it is not good at all for these particular transformations. Okay, so that means by one thing that we need to determine for all the transformation graphs is you have a data, and those data would look like a curve. It's not linear. Then you need to determine which action do you do. Do you do compress or do you do stretch? For this one, or once you decide, okay, I need to compress, do you compress the x values or do you compress the y values? So you do kind of like split into choosing what do I need to do to those x and y. Yep, next one. So if you try to so do the number 3 actions. So let's say the 3 action is our black here. If we try to stretch the x values, what would happen into this graph? All the x values would getting bigger and getting into further down. If you're looking at this, your graph, instead of liking to do straight line, you even more flatter and getting a bit longer to the other side. Yeah, the conclusion would be stretching x would not be a very good idea as well. This is definitely not a good move, as we don't get any good transformations. So if we don't have good transformation for doing stretch, what do we call stretch x values, then let's try to have a look at the last actions. The last actions would be talking about y. What color should I use? Gray. So the y is number 4 actions. Number 4, we're looking at this is stretching the y. You're increasing the y values. So if those the dots here get increased, moving all the way up, then what do you see of the new graph? Is more likely those black would be having a new up, right? Which one would that be? We don't do all 4 of them. We have to choose the one that make it more linear. Um, then try to give you one more example before we look at a bit further. The second example there would be going straight and suddenly, and you go jump all the way high. So instead of a good projections, supposed to go straight, it's no longer going straight. Instead of it, you're going up and then straight up down there. That become a exponential curve. For this exponential curve, we've got a problem data, which is the highlighted yellow there. Think about the action. Are we doing compress or doing stretch? Would help the data. If we try to do compressed, do you compress the x value or compress the y values? So if you try to compress, means you try to make it smaller. X compress is going towards to the 0. Y compress is going down. So if you think about the x there, if move across, all the things move across, it just make it more, it just make it worse. So you're looking at the graph going kind of making a circle going backward that way. That's definitely not linear. So we can basically jump into conclusion straight away. The first one, that doesn't help. The second one, if you try to compress the y, which is bring the y value down. So if you bring all the dots down a little bit, so here would be your new data, and your new data will make it a bit more linear because once you bring those data down. So that would be a good action that we can do. Yes, so compress y is a good option, not compressing x, right? Then how about we look at one more? So how about let's look at the other side. The other side we can do is stretch. Stretch. Can't spell today. Like always, S-T-R-E-T-C-H. If you try to do a stretch, the stretch can be do X or Y. Stretching means getting bigger. when you stretch x, you move away from the 0. When you stretch y, you're making it further up. The same thing, if you look at the y moving up, if all the value moving even further up, your graph would be just like boom, flying like a rocket, which is not a good option straight away. So we know that stretch y would not be good. What happened when you try to stretch x? We try to move those points a bit further down. So if you move those points a bit further down, you seems like that you becomes a bit more linear again. So both stretch the x and compress the y helps you to do a bit more linear. Then it's a good options for us to do, right? So now what and then what is compress and what is stretch? If you're looking at your book, that is from chapter 3, about chapter 3, page 150. It gives you quite a few example. There's a three kind of transformation you can choose from. The very first one is called quadratic transformation. Quadratic transformation. Quadratic transformation is an action of stretching. You try to stretch x or stretch y. If you take the square of x, means that you stretch the x value. We call this x squared transformation. If you try to do stretch, this is the number 1 and number 2 is x squared transformation. Number 3 and number 4, you can have the y square, means to stretch the y values. That is the y square transformations and y square transformations, right? So that one type, quadratics. The second one is basically called log and reciprocal. Logarithmic. I can't pronounce logarithmic. That's basically a compression. So when you try to do compress, you would have to either choose log or reciprocal transformation. And what does log means? Log means basically making those values smaller. If you take a log 100 with your calculator, it changes into 2. Log 1000, it changes into 3. You're making a big number into smaller one, that would be what we call log. When it's log or reciprocal, you change the value smaller. Compressed y value, you can either log x or 1 over x transformation. Think about which one is bigger, 10 or 1 over 10, or 100 or 1 over 100. If you take this reciprocal, means that you put a 1, you change a whole number into a fraction, which is just flip it the numbers. Then when you flip it, it changes into 1 over your particular value. And definitely if you try to make that 10 into 1/10, you make the value smaller. So both log and reciprocal would do the action of compress. And if you compress x, like this graph here, then log 10 or 1 over 8 would be your transformations. You can use compress y, bring them y down, which is log y or 1 over y. Okay, so that's not easy. I'm telling you, that's like definitely not easy. But yes, basically your job is to look at the graph and determine whether you're doing compress or doing stretch. Once you've got that, then we would try to do one thing. The next thing that we do after we have the transformations, let's say this particular example here, the transformation that we've got, it has a data as a temperature. The data of temperature x is 5, 10, 15, 20, 25 to 35, and 18, 10, 6, 5, 3, 2, 2. If we plot the graph, it looks like a curve coming down, and this is not the best values. We would like to do actions. When you try to do this as actions, the problem is the temperature value that is too further down. We can bring those value back if we try to compress the x value, then you would try to make it more linear. One of the action for compressing is reciprocal, 1 over x. You turn 1 5 into 1 over 5, and then 1 over 10, and 1 over 15. Once we've got this, according to the, if you plug this into your graph, you will able to find a new linear graph. And this linear graph, because it's more linear, then will give you a better projections. After you have a better projections, you substitute your values into it and do the exercise that you learned from last to last chapter. There's yeah, quite a few exercises you can do. It's all about linear graph. So I'd like you to give it a go on question 12 here. So question 12, for each of the following scalar blocks, suggest what would be the transformation we can do to make it work. So let's copy this graph. Question 12. Okay, we paste these three into it. Hopefully try to make it bigger. Okay, now it's a bit better. Okay, first of all, if you're looking at this, we can see this is a curve that way. What is the problem in this particular graph? We can see this, if we want to make it more linear, we can either make this one that way, make sense? Because you're stretching that one, or making that. To make this curve into a kind of a straight line, you can move that one down and move this one down, it becomes a straight line. So what action do we do? That one is doing sideways. Sideways is x, going back closer to 0. That means we try to compress x. And that one is moving down. Moving down means you want the y value become smaller. We compress y. Right? Compress x, compress y. When you compress x, you either do reciprocal or log x. Compress y is 1 over y or log y. So by doing those compressions, then this graph will become more linear. Okay, so for this one, we've seen this is getting more flattened. And the problem is this bunch here. And this bunch, if you try to draw this one, is more like that curve. Draw this curve here to make it more straight line. You can move this to, move this back, move the bottom part back, and move this up, and you'll become a straight line. Just like a bend, if you have a banded tubes, you want to strike it, you just open it up. So when you open this up, you know this one moving back is compress x, and you talk about this moving up, which is stretch y. For stretching y is y square actions. For compress x is 1 over x or log x. Okay, the last one, basically the same situation as A. You try to make this backward or make this up. Just like this, you want to turn it into a straight line, you do these two actions. Exactly the same as A, repeated. So hopefully you start finding a particular patterns here when you do a curve, which is a circle. If you're looking at the circle and chop this graph into 4 parts, sometimes you find a graph acting at on this pattern, sometimes you have a graph at this pattern, sometimes you have a graph running down that like this, and you have a graph running down that way. The 4 different parts. So instead, when you try to look at this as a circle, this it has to be these four types. It can't be anything else. If you looking at this, the transformation related to each of the graph, each of the situation, that one for a curve going that way, you want to make it a straight line. You're going that. Going backward, which is x compress. And moving up, y stretch. For the second situation, you want this one up, want that one open up. So both of them, x stretch and y stretch. Coming down here, you want that one going down, that one going down, going closer, which is x compress. That one going down, which is y stretch. That one going down and that one going big, that is x stretch. And the last one there would be y compress. So since there's always these four options, and once you've got the graph, identify which option would that be, then you'll be able to determine whether you do stretch or compress. Wherever you stretch, just put square at the top. So that's y square. Straight away, y square that you do. That one, y stretch, y compress. What have I done? Going down. That one is y compress. So, and then when you try to look at the x stretch, that one there, put the x square there. Put the x square there. Then once we find the x compress, 1 over x, x compress 1 over x, and then y compress 1 over y. Do we have y compress? Another y compress 1 over y. There's two options for compressed, either 1 over x or log x, or log x. That one or log y. That one or log y. So hopefully, by doing this, I'll give you some ideas. When you do transformation, you can do lots of different actions, and I'd like you to do a few example with Excel. So once you know, like, just do if you have a list, then you try to get every single entry with that transformations. You plot a new graph. Once you have the new graph, we're going to find out the equation for the new graph and do the projection after. Okay, that's all about transformations. Hope it helps, and yeah, try to do some more questions on chapter 3. Can't remember this one. That is 3.9 transformations, right? So try to do some of them and get used to those concepts. Okay, thank you. Bye.